Hello all, welcome everyone to the problem solving session of thermodynamics course from NPTEL. I am one of the TA of this course, myself Pradeev E. Today I have some problems with entropy generation and then Rankine power cycles and other air standard cycles. The first problem is on the screen. A room is maintained at 27 degrees Celsius while the surroundings are at 2 degrees Celsius. The temperature of the inner and outer surface of the wall with thermal conductivity of 0.71 watt per meter Kelvin are measured to be at 21 degrees Celsius and 6 degrees Celsius respectively. Heat flows steadily through the wall 5 meters. The wall with a cross-section area of cross-section area of 5 meters cross 7 meters and a thickness of 0.32 meters. Determine the rate of the heat transfer through the wall, the rate of entropy generation in the wall, and the rate of total entropy generation with this heat transfer process. So let me draw the schematic of this system given in the problem. So there is a wall with a thickness of 0.32 meters, and the inside of the one side of the wall is the room and the other side is the surroundings. Then the room temperature is 27 degrees Celsius, and surrounding is at 2 degrees Celsius. So now the heat transfer occurs over the wall, and we assume a linear temperature across the wall, so it is represented by a slant line, and then the surface temperature at the wall is given as 21 degrees Celsius and 6 degrees Celsius, and the cross section area is given as 5 cross 7, so I write area as 35 meters square. Now we have to determine the rate of heat transfer through the wall, the rate of entropy generation, and the total entropy generation. So for entropy generation we need to have all the temperatures in Kelvin, so I am converting the temperatures to Kelvin. So for 2 degrees Celsius it will be 275 Kelvin, and for 27 it is 300 Kelvin. For 21 degrees Celsius it is 294 Kelvin, and for 6 degrees Celsius it is 279 Kelvin. So now the first problem is to find the heat transfer. So heat transfer is given by Q is equal to Ka into delta T by delta X. Here K is given as 0.71 watt per meter Kelvin, and area we know it is 5 cross 7, which is 35, and then we have delta T, which is 21 minus 6. I am writing delta T in terms of degree Celsius because it will be the same even if I write it in terms of Kelvin, and then divided by delta X. So here delta X is the thickness of the wall, which is 0.32. So this is 1164.8 watts. So we have found the heat transfer. Now we need to find the rate of entropy generation in the wall. So across the wall we need to find the rate of entropy generation. So entropy generation or total entropy change is given by ds1 by dt is equal to rate of heat transfer So this is delta of q dot of T. So we have two heat transfers across the wall. So the heat transfer to the wall occurs at 21 degrees Celsius or 294 Kelvin, and heat transfer out of the wall occurs at 279 Kelvin. For both the cases, the heat transfer is only 1164.8. So I can write for Q in, I write 1164.8, which occurs at 294 Kelvin minus 1164.8 divided by 279 Kelvin. So this is minus 0.213 watt per Kelvin. And similarly, that means entropy generation through the wall is 0.213 watt per Kelvin. And similarly, I can calculate the total entropy generation. So that is given by Ts of dT total. It is the same Q by T, and we have 1164.8 divided by the room temperature. Room temperature is 300 Kelvin, and temperature heat transfer to the ambient or the environment is occurring at 2 degrees Celsius, which is 275 Kelvin. So this way I can calculate entropy generation. So here I have 0.353 watt per Kelvin. So total entropy generation, the rate of total entropy generation is 0.353 watt per Kelvin. Moving on to the next problem, I have there is a 200 meter cube rigid tank which contains compressed air at 1 megapascal and 300 Kelvin. Determine how much work can be obtained from this air if the environmental conditions are 100 kilopascal and 300 Kelvin. So this is a problem with availability. So we are asked to find the availability of the tank with the compressed air. So availability is given by this formula, where phi availability is change in internal energy. So internal energy of the U represents internal energy of the system, U naught represents the internal energy of the dead state. So this has to be calculated at ambient temperature. So it can be written as CV T naught, and this is a P naught, V minus V naught. So here P naught is ambient pressure again, and V is a specific volume of the system, and V naught is a specific volume at dead state, V naught. And then we have T naught, temperature of the ambient, and then S minus S naught is entropy change during entropy change between the system and the surrounding, or entropy change at temperature at the given system temperature, and minus the entropy of the system at dead state, at temperature of the dead state, which is 300 Kelvin here, and then plus the kinetic energy plus the potential energy. So in this problem there is no change in temperature, so we can assume u minus u naught is 0, and since the pressure is changing from 1 megapascal to 100 kilopascals, there will be some change in specific volume, so that has to be taken into account. I would write this as 0, this exists, and T naught is 300 Kelvin, but S minus S naught for a process with changing pressure can be calculated, and since there is no mention of the kinetic and potential energy, I assume this to be 0. So we are left with only the two terms. So first I have to calculate the mass of the system. So this is availability for unit mass of the system, so I can calculate mass, total mass. So M is given by PV by RT. So here pressure is 1 megapascal, or 1 into 10 power 6 pascals, into volume is 200 divided by R. So it is, since it is air, it is given as air, we can take R as 287 into temperature is 300 Kelvin. So you can calculate the mass this way. So which is 2322 or 23. kg. Now I can calculate P naught into V minus V naught. So the V is given by PV equal to MRT relation. So I initially will calculate for the unit availability for the unit mass, and then finally multiply with the mass to calculate the availability of the total system. So I have V as RT by P. So that means here the P naught is 100 kilopascal. So we have in SI units 100 into 10 power 3 into V is R T by P minus R T naught by P naught. So again we can take R as constant, which is 287. We have 287 into 100 into 10 power 3 multiplied by we will have T by P inside the bracket. So temperature is 300 Kelvin for the system, and pressure is 1 megapascal, which is 10 power 6 minus, again dead state temperature is 300 Kelvin, and P naught for the dead state is 100 into 10 power 3, 100 kilopascals. So calculating this, so P naught into V minus V naught is minus 77,490. So this is joules. We had everything in SI units itself, so it is joule per kg. We have calculated only per unit mass. And similarly we had T naught into S minus S naught. So S minus S naught for is generally given by this expression Cp ln T by T naught minus R ln of P by P naught. So here this expression becomes 0, T by T naught is same. So we have T naught as 300 Kelvin multiplied by minus of R is 287 ln of P by P naught, which is 10 power 6 divided by 100 into 10 power 3. So we have 198 252 joule per kilogram. So this has a negative sign here, and yeah, so we have P naught V minus B naught minus T naught of this. So availability is minus 77,490 minus into minus of 198 252. So this is this is 12762 joules per kilogram, or it is 120.76 kilojoules per kg. So for the total system, we had a mass of 2332. So we have total availability equal to mass into 5. So this is 2323 into 120.76. This will become 280,525 kilojoules, or 280.5 megajoules. So this is how we calculate the availability of a given system. So the next problem is with the Rankine cycle. So here a steam at 20 bar 360 degrees Celsius is expanded in a steam turbine to 0.08 bar. It then enters a condenser where it is condensed to saturated liquid water. The pump feeds back the water into the boiler. Assuming ideal processes, find the per kg of steam, the net work and the cycle efficiency. If the turbine and the pump have each 80% efficiency, find the percentage reduction in the net work and cycle efficiency. So a simple Rankine cycle is given, representing that in TS diagram. We have the vapor dome, and steam at 20 bar 360 degrees Celsius should be a superheated state, and then we have something like this condensing to 0.08 bar, and this is pumped. Feed water is pumped to the boiler, and with the boiler it should enter at 20 bar and then gets heated up to this state. So we say this state 1, this as state 2. I say this as state 2, yes, assuming isentropic process. Then we have 3, we have 4, and there will be actual process will be, sorry, this is 4s and actual 4 will be somewhere here. So that is with considering the efficiency of the pump and the turbine. So here we have considered the efficiency of the pump. Considering the efficiency of the turbine, it will go somewhere like this, and right here. So this is 0.2. So now we can calculate the enthalpy at the different points using the steam table. We can calculate H1 we can see the value of H1 first. So H1 is at 20 bar pressure and 360 degrees Celsius. Moving on to the steam table, first we need to check if it is in the saturated if it is within the saturated dome, or it is a superheated vapor. So for finding that, we have this saturated water table. Here on the first column is pressure in megapascal. So for 20 bar as given in the problem, we have 2 megapascals. So for 2 megapascal is here, and the saturation temperature at 2 megapascal is 212 degrees Celsius, whereas in the problem it was given as 360 degrees Celsius. So it is in a superheated state. So we can go to the superheated steam table. So for 20 bar we have 2 megapascals, and 2 megapascal appears here. So I will zoom in for okay. This our temperature is 360, but we have only 350 and 400 degrees Celsius, so we have to interpolate these values. So I would do this. Here we have enthalpy. Okay, we have to get the enthalpy and the entropy values. So first we would note down the enthalpy values given in the table and then try to interpolate. So at 350 it is 3137.7. So I would write down here 350 3131.7. Right. Sorry, 3137.7. So this is 7. And at 400 Kelvin, sorry, degrees Celsius, we have 3242.3. So interpolating for 360, so this interpolation maybe I will do it once. So we take the line equation, y minus y1 by y2 minus y1 is equal to x minus x1 by x2 minus x1. So here we assume temperature is temperature is x and y is enthalpy. We can write this as H1, or the enthalpy at first state is enthalpy. So here I take this as 1 and this as 2 for the interpolation. Y1 is 3137.7 divided by y2 minus y1, which is 3242.3 minus 3137.7. So this is equal to x is 360 for us, at which we need to find the values, enthalpy value, and x1 is 350, x2 is 400 minus 350. So we have H1 is equal to, so this is 10 by 50, which is 1 by 5 into, we have this difference 3242.3 minus 3137.7 plus we have this value which is 3137.7. So we have got 3158.62 kilojoule per kg. So I will note down here enthalpy at first state is 3158.6 kilojoule per kg, and we can calculate entropy at second state also. For entropy we have 6.958 and 7.129. So entropy 6.958 7.129. So this is at 350 degrees Celsius and this is at 400 degrees Celsius. So now we need to calculate for 360. So this is 6.9922. So this is enthalpy at state 1, and this is also same as enthalpy at state 2 S process, so that means ideal process. So for both of this we have 6.9922 kilojoule per kg Kelvin. I will also okay, now we have the condenser temperature at the condenser, which is 0.08 bar. So we can get the enthalpy and entropy at these states. So for 0.08 bar, it should be we are not sure if it is within the vapor dome or outside the vapor dome. So if it is 0.08 bar, it should be 0.008 megapascal. We have this entropy. Our entropy value was entropy is 6.9922, and we see for the saturated vapor the entropy value is 8.227, and for the saturated liquid it is 0.5925. So our entropy value lies within these two values, so that means it falls within the vapor dome. So we can calculate the steam quality or dryness ratio. So we have this S2S is equal to SF2 plus steam dryness fraction for ideal state, ideal turbine, and then multiplied by Sg at second state. So this is 0.5925, 0.5925 plus dryness fraction, and on the left hand side we had 6.9922, and for Sg2 we have, this should be Sfg2, so that is difference in the entropy between the liquid and the vapor state. So that is 7.6348. 7.6348. So dryness fraction can be calculated here. Now we have 6.9922 minus 0.5925 divided by 7.6348. So this is 0.838. So with this we can also calculate the enthalpy at second state ideal one. So that I call as enthalpy 2s. So this is F2 plus dryness fraction at this state. So that is H2s multiplied by latent heat of enthalpy HFG for the second state. So these values I can get it from the steam tables. So that is 173.8 and 2402.4. 173.8 plus dryness fraction is 0.838 into 2402.4. So this is 2187 kilojoule per kg. This is H2s. So now we have calculated the ideal enthalpy at the end of turbine. Now we were given the this efficiency of the turbine, which is 80%. Yeah, we have efficiency as 80%. So we can write the efficiency of turbine as H1 minus actual enthalpy change or actual work extracted from the steam divided by ideal work that can be extracted from the steam turbine. So here actual work that can be extracted will be more than the ideal work that can be extracted will be more than the actual work. So in the efficiency formula that lies in the denominator. So this is given as efficiency is given as 0.8, and H1, we know H1 and H2s, so with that we can calculate H2. So H1 is 3158.6 minus H2 divided by 3158.6 minus 2187. So which means H2 is equal to we have 3158.6 minus 777.28. So we have 2381.32. So this unit is kilojoule per kg Kelvin. Sorry, kilojoule per kg. So we have got the enthalpy for the actual turbine. Now we can calculate the pump parameter. So we don't have the inlet enthalpy, but inlet enthalpy is not needed. All we for the pump work. So pump work can be written as V into P delta in change in pressure. So our from the drawing we had 3 and 4 are the so we have P4 minus P3. So this can be taken at state 3. So state 3 is again 0.08 bar. We can go to the steam table for 0.08 bar. This is the volume of the liquid, which is 0.00 to 1009. So we have 0.001009 into change in pressure. So we had 20 bar writing in SI units, and then we had 0.08 bar in SI units. So this is 2009 or approximately 2010 kilojoule per kg. So this is the ideal turbine pump work. Calculating the actual work, we will need the efficiency values. So efficiency of the pump is here. Actual work will be higher, so that goes in the denominator, and ideal work will be on the numerator. So that means we have 0.8 is equal to ideal work is what we have calculated now, and then actual divided by the actual work. So WP is 2010 by 0.8. We have 2512 kilojoule per kg. So we have calculated the actual and ideal work of the pump. Now we will need the enthalpy at this higher pressure. So that is the entry of the boiler can be 4s or 4. This we can approximate that this is the same, and it is at the saturation line, or we can also add enthalpy from this H3 point. H3 plus the work done by the pump will go into the steam or the liquid at state 4. So I think we can do that way. So enthalpy at 3 we have calculated H3. No, I think H3 can be obtained from this table. So H3 is enthalpy of the liquid at saturated liquid at 0.008 per megapascal, which is 173.8. So I'm still wondering if this pump work is this high enough, because in the we didn't get so much turbine work. So now we need to calculate the enthalpy at state 4. That I assume that it is enthalpy of the liquid at 20 bar, so which is 2 megapascal. So that is 908.5 kilojoule per kg. So I write H4. H4 is 908.5 kilojoule per kg. Now we know heat transfer to the furnace or the boiler is H1 minus H4, so that is we had 3158.6 3158.6 minus 908.5 divided so this is so we have 2250.1 kilojoule per kg Kelvin, and turbine work is I think so this is not in kilojoules. We have meter cube here, and we have Pascal here, so this is in SI unit, so this is kilojoule, sorry, it's joule per kg, so that means it is only 2.01 kilojoule per kg. So all other terms we had in kilojoule, so that is why we saw a very high value here. This is 2.512 kilojoule per kg. So in that case we can also calculate H4 as H3 plus this pumping work. So H3 was so H3 we had here, so it is 173. Yes, so it would be the right way to do because H3 is 173.8. So this is H3 plus pumping work, so this is 173.8 plus we have 2.01 or for the H, so this is for S value, and for H4 we have 173.8 plus 2.5. Why? Because first I have taken the enthalpy at the vapor on the saturated line, but we can see here, but this is a subcooled liquid, so there will be some latent heat to be supplied to the water so that it becomes saturated water. So now we have H4. H4s can also be calculated, so I will do it here. So this is 175.81. For H4 we have 176.31. so anything related to the pump will be very minimal, so the WP and WPS doesn't make much difference in the total cycle efficiency or total cycle parameters. So both of them are in kilojoule per kg. And for calculating the heat added by the furnace, we have H1 minus H4, and H1 is 3158.6, and H4 we have just calculated, it is either 176.31 or 175.81, so I will roughly take 176. So now we have this as 2982.6 kilojoule per kg. Now we have turbine work. For turbine work we have this value, so 3158.6 minus 2381, 3158.6. so we already have, so we have both turbine, isentropic turbine, and also turbine with an inefficiency. Both we have 3158. So I would write the expression. We have H1 minus H2s, or for the actual turbine we have H1 minus H2. So both 3158.6 minus H2s is 2187, and for H2 it is 2381.3. So turbine work isentropic is 971.6 kilojoule per kg, and actual turbine work is 777.3. So we have calculated the turbine work, and we have the heat added by the boiler. Now we can calculate the cycle efficiency. So cycle efficiency, ideal cycle efficiency is turbine work idled by Qn, and for actual cycle efficiency we have turbine work by Q. So ideal turbine work is 971.6 divided by heat added is 2982.6, and here we have the same 2982.6, and for the actual turbine work it is 777.3. This is 26.06%. And this one is 32.6%. So we have calculated cycle efficiencies. If we can see, if we were asked to find something else, assuming ideal process, find the per kg the net work and the cycle efficiency. So we have calculated the net work and the cycle efficiency, and we have also calculated the parameters with assuming turbine and pump work as 80%. Turbine out is here 971 and 777 kJ per kg, and cycle efficiency is 26 and 32%. We have only 8 minutes left, and I'm not sure if I can complete this problem. I will try. In an air standard diesel cycle, the compression ratio is 16, and the beginning of isentropic compression, the temperature is 15 degrees Celsius, and the pressure is 0.1 megapascal. Heat is added until the temperature at the end of the constant pressure process is 1480 degrees Celsius. Calculate the cutoff ratio, the heat supplied per kg of air, and the cycle efficiency and mean effective pressure. So we can draw the air standard cycle. We have isentropic compression, represented by a curve in the PV diagram, and then we have constant pressure heat addition, and then it expands, and then there is a constant volume heat rejection. So assume starting with 1 for the dead state, we have compression represented by 1 2, heat addition represented by 2 3, and expansion represented by 3 4, and heat rejection is represented by 4 1. Now we know, I can write the known parameters. T1 is 15 degrees Celsius, or in terms of Kelvin, this is 288 Kelvin, and P1 is 0.1 megapascal, or 10 power 5 pascals. And heat is added at the end of constant pressure processes. And the temperature at the end of constant pressure process is 1480 degrees Celsius. So at the end of constant pressure process is third state. So T3 is given as 1480 degrees Celsius. This is 1753 Kelvin. These are the inputs to the problem, and the compression ratio is also given as 16. So that is V1 by V2 is 16. We have to calculate the cutoff ratio and the heat supply. So we can start calculating states at the parameters at each state. So properties at each state. So for second state, we can calculate the pressure using the isentropic process. So for isentropic process, we have PV power n is equal to constant. So that is P2 equal to P1 into V1 by V2 power n. So or gamma for the isentropic process. So we have P2 is equal to P1 by V2 power gamma, and P1 is 10 power 5 pascals. V1 by V2 is given as 16, and for air we can take gamma as 1.4. So this becomes 4.85 into 10 power 6 pascals. So P2 is 4.8 megapascal, and we can calculate T2. So we know PV power T is equal to mR, which is constant because both the composition and mass doesn't vary in a standard cycle. So we can write P1 V1 by T1 is equal to P2 V2 by T2. So this means T2 is P2 V2 by P1 V1 into T1. So this is P2 by P1 can be calculated, so that is 48.5 because P2 is 4.85 into 10 power 6 and P1 is 10 power 5, and then V2 by V1 is 1 by 16, so we have by 16 into T1 is 288 Kelvin, so T2 can be calculated. Which is 873 Kelvin. T2 is 873 Kelvin. And now heat is added in the process 2 to 3, which is given by Cp into T3 minus T2. So T3 is given in the problem as 1753 Kelvin, and we know Cp of air is 1.005 kilojoule per kg Kelvin, and sorry, T3 is 1753 minus T2 is 873. So this is 884.4 kilojoule per kg. So this is the heat added, which is one of the questions in the problem. And then we need to calculate the cutoff ratio, which is V3 by V2. So we need to calculate volume at 3. Again, we can use PV by T relation. So we have P2 V2 by T2 is equal to P3 V3 by T3. Here both the pressures are same, the constant pressure process, and we have V3 by V2 is equal to T3 by T2, which is 1753 by 873. So cutoff ratio is 2. It's exactly 2.0. So cutoff ratio heat supplied per kg of air is also calculated. Now we need to calculate the cycle efficiency. So cycle efficiency is work output net work divided by heat supplied. So since I am out of time, I will just explain how to calculate this. To calculate the net out, we can calculate the work done during expansion. So work done during constant pressure process is area under the curve. So that is pressure into V3 minus V2, or let's just write down here. So W net is equal to W23 plus W34 minus compression work, which is W122. So this is a constant pressure process. We have pressure into difference in volume, and for 3, 4 and 1, 2 process we have isentropic compression and expansion. So we have this relation work done during isentropic process equal to P1 V1 minus P2 V2 by gamma minus 1. So this is a formula to be used to calculate the isentropic work during compression and expansion. Then so that's how we get the net work, and heat supplied is already calculated, so that is 884.4 kilojoules per kg. So using these things we can calculate the cycle efficiency. And to calculate the MEP is given by work output or net work divided by swept volume. So that is, again, this W net is just calculated above, and the swept volume is V1 minus V2. Using this we can calculate the mean effective pressure as well. So I hope you will be able to solve this problem. If you have any questions, you can ask in the discussion forum. Thank you for attending the course. I think this is the last problem solving session and last week of the course. Thank you for attending the course. I hope this course would have helped you. If you, I think there are many feedback forms which will help us understand your state of mind during the course. Thank you. I will close this session.